but not even relaxed, affluent Princeton could help Gödel finally escape his demons. Einstein was always full of laughter. He described Princeton as a banishment to paradise. But the much younger Gödel became increasingly solemn and pessimistic.
Slowly, this pessimism turned into paranoia. He spent less and less time with his fellow mathematicians in Princeton. Instead, he preferred to come here, to the beach next to the ocean, walk alone, thinking about the works of the great German mathematician Leibniz.
But as Gödel was withdrawing into his own interior world, his influence on American mathematics, paradoxically, was growing stronger and stronger. And a young mathematician from just along the New Jersey coast eagerly took on some of the challenges he posed.
2, 3, 4, 5, 6, 7, 8, 9, 10 times a day I could love you.
In 1950s America, the majority of youngsters weren't preoccupied with mathematics. Most went for a more relaxed, hedonistic lifestyle in this newly affluent land of ice cream and donuts. But one teenager didn't indulge in the normal pursuits of American adolescence, but chose instead to grapple with some of the major problems in mathematics. From a very early age, Paul Cohen was winning mathematical competitions and prizes. But he found it difficult at first to discover a field in mathematics where he could really make his mark. Until he read about Cantor's continuum hypothesis. That's the one problem, as I'd learned back in Halle, that Cantor just couldn't resolve. It asks whether there is or isn't an infinite set of numbers bigger than the set of all whole numbers, but smaller than the set of all decimals. It sounds straightforward, but it had foiled all attempts to solve it since Hilbert made it his first problem way back in 1900. With the arrogance of youth, the 22-year-old Paul Cohen decided that he could do it.
Cohen came back a year later with the extraordinary discovery that both answers could be true. There was one mathematics where the continuum hypothesis could be assumed to be true.
There wasn't a set between the whole numbers and the infinite decimals.
But there was an equally consistent mathematics where the continuum hypothesis could be assumed to be false.
Here, there was a set between the whole numbers and the infinite decimals. It was an incredibly daring solution. Cohen's proof seemed true, but his method was so new that nobody was absolutely sure. There was only one person whose opinion everybody trusted.
There was a lot of skepticism, and he had to come and make a trip here to the Institute right here to visit Gödel, and it was only after Gödel gave his stamp of approval in quite an unusual way said, give me your paper, and then on Monday he put it back in the box there saying, yes, it's correct. Then, of course, everything changed.
Today, mathematicians insert a statement that says whether the result depends on the continuum hypothesis. We've built up two different mathematical worlds, in which one answer is yes, and the other is no. Paul Cohen really has rocked the mathematical universe. It gave him fame, riches, and prizes galore.
He didn't publish much after his early success in the 60s. But he was absolutely dynamite. I can't imagine anyone better to learn from. And he was very eager to learn, to teach you anything he knew, or even things he didn't know.
With the confidence that came from solving Hilbert's first problem, Cohen settled down in the mid-1960s to have a go at the most important Hilbert problem of them all, the eighth, the Riemann hypothesis. When he died in California in 2007, 40 years later, he was still trying. But like many famous mathematicians before him, Riemann had defeated even him. But his approach has inspired others to make progress towards a proof, including one of his most famous students, Peter Sarnak.
I think overall, absolutely, I love the guy. It was my inspiration. I'm really glad I worked with him. He put me on the right track.
Paul Cohen is a good example of the success of the great American dream. Second-generation Jewish immigrant becomes top American professor. But I wouldn't say that his mathematics was a particularly American product. Cohen was so fired up by this problem that he probably would have cracked it whatever the surroundings.
Paul Cohen had it relatively easy. But another great American mathematician of the 1960s faced a much tougher struggle to make an impact. Not least because she was female. In the story of maths, nearly all the truly great mathematicians have been men. But there have been a few exceptions. There was the Russian Sofia Kovalevskaya, who became the first female professor of mathematics in Stockholm in 1889 and won a very prestigious French mathematical prize. And then Emmy Noether, a talented algebraist who fled from the Nazis to America, but then died before she fully realised her potential. And then there is the woman whom I'm crossing America to find out about, Julia Robinson, the first woman ever to be elected president of the American Mathematical Society. She was born in St. Louis in 1919, but her mother died when she was 2. She and her sister Constance moved to live with their grandmother in a small community in the desert near Phoenix, Arizona.
Julia Robinson grew up somewhere around here. I've got a photo which shows her cottage in the 1930s with nothing much around it. And the mountains pretty much match those over there, so I think she might have lived just down there.
Julia grew up a shy, sickly girl, who when she was 7 spent a year in bed because of scarlet fever. Her ill health persisted throughout her childhood. She was told she wouldn't live past 40. But right from the start, she had an innate mathematical ability. Under the shade of the native Arizona cactus, she whiled away the time playing with endless counting games with stone pebbles. This early searching for patterns will give her a feel and love of numbers which would last for the rest of her life. But despite showing an early brilliance, she had to continually fight at school and college simply to be allowed to keep doing mathematics. As a teenager, she was the only girl in the maths class, but had very little encouragement. So the young Julia sought intellectual stimulation elsewhere.
Julia loved listening to a radio show called The University Explorer, and the 53rd episode was all about mathematics. The broadcaster described how he discovered that despite their esoteric language and their seclusive nature, mathematicians are the most interesting and inspiring creatures. For the first time, Julia had found out that there were mathematicians, not just mathematics teachers, that there was a world of mathematics out there, and she wanted to be part of it.
The doors to that world would open here at the University of California at Berkeley near San Francisco.
She was absolutely obsessed that she wanted to go to Berkeley, or not to Berkeley, she wanted to go away, someplace where there were mathematicians.
Berkeley certainly had mathematicians, including a number theorist called Raphael Robinson. In their frequent walks around the campus, they found that they had more than just a passion for mathematics. They married in 1952. Julia got her PhD and settled down to what would turn out to be her lifetime's work, Hilbert's 10th problem.
She thought about it all the time. She said to me she just wouldn't want to die without knowing that answer, and it had become an obsession.
Julia's obsession has been shared with many other mathematicians since Hilbert had first posed it back in 1900. His 10th problem asked if there was some universal method that could tell whether any equation had whole number solutions or not. Nobody had been able to solve it. In fact, the growing belief was that no such universal method was possible. How on earth could you prove that however ingenious you were, you'd never come up with a method? With the help of colleagues, Julia developed what became known as the Robinson hypothesis. This argued that to show that no such method existed, all you had to do was to cook up one equation whose solutions were a very specific set of numbers. The set of numbers needed to grow exponentially, like taking powers of 2, yet still be captured by the equations at the heart of Hilbert's problem. Try as she might, Robinson just couldn't find this set. For the 10th problem to be finally solved, there needed to be some fresh inspiration. And that came from 5,000 miles away, St. Petersburg in Russia.